The reactivity series of metals is a ranking of metals based on their relative reactivity with other substances, particularly with water and acids. It helps predict the likelihood of a metal reacting with a given substance and the ease with which it can displace other metals from their compounds. The series is a fundamental concept in chemistry and is crucial in understanding various chemical reactions, particularly those involving metals. The reactivity series is typically presented in a descending order of reactivity, with the most reactive metals at the top and the least reactive ones at the bottom. Here's a typical reactivity series: potassium, sodium, calcium, magnesium, aluminum, zinc, iron, nickel, tin, lead, hydrogen, copper, mercury, silver, gold, and platinum. The reactivity of metals is primarily determined by their ability to lose electrons to form positive ions cations. Metals with low ionization energies tend to be more reactive because they can easily lose electrons to form positive ions. The reactivity also depends on the metal's ability to displace other metals from their compounds. Metals that can more easily displace other metals from their compounds are considered more reactive. Some key aspects of the reactivity series are potassium, sodium, and calcium. These metals are highly reactive and can react vigorously with water to form hydroxides and release hydrogen gas. They are stored under oil to prevent contact with moisture in the air. Magnesium and aluminum. These metals are reactive, but not as much as the alkali metals. They react with acids to produce hydrogen gas and with steam to form oxides. Zinc, iron, and tin. These metals are moderately reactive. They react with acids, although more slowly than the more reactive metals. Zinc and iron can displace hydrogen from dilute acids. Tin reacts slowly with hydrochloric acid. Lead, hydrogen, copper, mercury, silver, gold, and platinum. These metals are less reactive and do not readily react with acids or water at room temperature. However, some of them can react under specific conditions. For example, copper can react with concentrated nitric acid, and gold and platinum are highly unreactive, making them suitable for various applications, including jewelry and corrosion-resistant coatings. The reactivity series is a useful tool for predicting the outcomes of various chemical reactions involving metals. It helps chemists understand and predict the behavior of metals in different chemical environments and is particularly important in industries such as metallurgy, where metals are processed and used in various applications. Position of carbon in reactivity series. Carbon does not have a fixed position in the reactivity series of metals because it is not a metal. Instead, carbon is a non-metal and thus doesn't fit into the typical reactivity series where only metals are listed. However, carbon's reactivity can be compared to that of metals and other non-metals in various contexts. Carbon exhibits a range of reactivities depending on the form in which it occurs. Here are some key points about the reactivity of carbon. These are two allotropes of carbon. Graphite is relatively unreactive and is often used as a lubricant and in tensile leads due to its low reactivity. Diamond is highly unreactive and is one of the hardest substances known. Carbon forms the basis of organic chemistry and participates in a vast array of reactions, forming strong covalent bonds with other elements such as hydrogen, oxygen, nitrogen, and halogens. These reactions typically involve the sharing of electrons rather than the transfer of electrons as seen in metal reactions. Carbon can react with oxygen to form carbon dioxide or carbon monoxide. These reactions are not as vigorous as those of highly reactive metals, but are nonetheless important in various industrial processes and combustion reactions. In some instances, carbon can react with metals to form carbides, such as calcium carbide or iron carbide. These reactions typically occur at high temperatures and involve the formation of strong covalent bonds between carbon and the metal. In the context of redox reactions, carbon can act as either an oxidizing agent or a reducing agent, depending on the reaction conditions and the substances involved. For example, in the extraction of metals from their oxides through reduction with carbon smelting, carbon acts as a reducing agent by donating electrons to the metal oxide. In summary, carbon's reactivity cannot be neatly placed within the reactivity series of metals due to its non-metallic nature. However, its reactivity can be understood in terms of its ability to form strong covalent bonds with other elements and its role in various chemical reactions, including those involving metals, oxygen, and organic compounds. The reactivity series is a concept in chemistry that ranks metals and sometimes non-metals in order of their reactivity. This ranking is based on how readily the elements undergo chemical reactions, particularly with acids and water. The series is typically arranged with the most reactive element at the top and the least reactive at the bottom. Reactions of metals based on reactivity series. Potassium is highly reactive and reacts vigorously with water to produce hydrogen gas and potassium hydroxide. Sodium also reacts violently with water to produce hydrogen gas and sodium hydroxide. Calcium reacts less vigorously with water, producing hydrogen gas and calcium hydroxide. Magnesium reacts slowly with cold water, but more rapidly with hot water, producing magnesium hydroxide and hydrogen gas. Aluminum does not react with water due to the protective oxide layer on its surface. Zinc reacts with water only when steam is passed over it, producing zinc oxide and hydrogen gas. Iron reacts slowly with steam to form iron oxide and hydrogen gas. Lead does not react with water under normal conditions. Copper does not react with water or steam under normal conditions. Silver does not react with water or steam under normal conditions. Gold does not react with water or steam under normal conditions. Reactions of nonmetals based on reactivity series. Nonmetals are not commonly arranged in a reactivity series like metals because their reactivity tends to vary widely depending on the specific conditions. However, some nonmetals can be broadly categorized based on their reactivity. Halogens are highly reactive. Nonmetals. Fluorine is the most reactive of all the elements and readily reacts with most other elements. Oxygen is also highly reactive, especially with metals, forming metal oxides. Nitrogen is relatively unreactive under normal conditions, but it can form compounds with certain elements under specific conditions. Carbon is versatile and can form compounds with a wide range of elements, but its reactivity depends on the form, example graphite, diamond, or carbon compounds. Noble gases are generally inert and do not readily undergo chemical reactions under normal conditions. Overall, while the reactivity series is more commonly discussed for metals, understanding the reactivity of nonmetals is also important in various chemical contexts, especially in understanding their role in forming compounds and their interactions with other elements. Uses of reactivity series. The reactivity series, also known as the activity series, is a list of metals arranged in order of their reactivity from highest to lowest. It's a useful tool in chemistry with several practical applications. The reactivity series helps predict whether a metal will displace another metal from its compound in a single displacement reaction. A metal higher in the series can displace a metal lower in the series from its compound. In electrochemistry, the reactivity series helps in understanding and predicting the behavior of metals in galvanic cells or voltaic cells. Metals higher in the series tend to be more reactive and thus are more likely to undergo oxidation, while those lower in the series tend to be reduced. Knowing the reactivity series is helpful in understanding why certain metals corrode more readily than others. Less reactive metals are less likely to corrode when exposed to the environment compared to more reactive metals. Therefore, The Reactivity series guides material selection for applications where corrosion resistance is important. In metallurgy, the Reactivity series plays a crucial role in determining the method of extraction of metals from their ores. Metals high in the Reactivity series, such as sodium, magnesium, and aluminum, are often extracted by electrolysis, while metals lower in the series, like copper and silver, can be extracted by reduction with carbon or hydrogen. The Reactivity series is commonly used in educational settings to teach students about the concept of chemical reactivity and its applications in various chemical processes. It provides a framework for understanding the behavior of metals in different chemical reactions. Understanding the Reactivity series is important in various industrial processes, such as metal refining, alloy production, and chemical manufacturing. It helps in selecting appropriate materials and optimizing reaction conditions for desired outcomes. Overall, the Reactivity series serves as a fundamental concept in chemistry, providing insights into the behavior of metals in various chemical reactions and facilitating the design and understanding of chemical processes in both academic and industrial settings.